So that was from earlier, so we're good. Thank you.
Okay, wonderful. All right, guys. So the topic today is a new topic. Let's recap what we have done so far. We have had through one round of recap. So we said that you can use neural vector embeddings. That's a new term. What does neural vector embeddings mean? It means that we have used a transformer encoder. If you want a concrete example, think BERT, then given it a contrastive loss function, a Siamese network, in which we give it a triplet, a, a text, a similar text, and an irrelevant text. And what we asked the machine to do was minimize the distance, the vector distance between. So as those texts become token IDs, become token vectors, then go through the transformer layer and they have cross attention, each one of them paying attention to each other, or the self attention more technically. So the right word to use is as those tokens get contextualized. More concretely, as the word bank realizes that the sentence is the boat on the other on the river bank, right? So from the sentence, that bank word realizes that I must be about the river bank, not about the financial bank, right? So as the tokens get contextualized, they come out as vectors at the other end of the transformer, of the encoder. As they come out as vectors at the other end, now comes the question, what do we do? Each of the tokens have become vectors. There are usually two ways of dealing with it. One is called pooling, and one is called taking a special token. That's the CLS token. And with the CLS token, remember the special token at the beginning, you basically say the token itself has no meaning. So if it gets contextualized, what is it picking up? It's trying to pick or find its meaning from all the other words in the sentence, isn't it? And therefore, in a way, it knows about all the meaning of the entire sentence. So you take that token's vector and you say, this is the embedding vector. That is approach one. People have alternatively also tried taking mean pooling. They can take the average of all the vectors that were produced and say, okay, let's consider all these vectors together as that. Now, this is called one vector approach. So I want to now take you to the next stage. What I taught you when we said vector embedding, this is by far the most popular way of doing vectors, converting text to vectors, semantic vectors, right? Semantically meaningful vectors. However, as you will learn in the course of time, this is not the only way that you can create vectors. Yeah. Yes, yes. I'll come to. I haven't shared anything yet. Yeah. So just listen to me, guys, at this moment. Huh? So you get contextualized vectors, one vector per text. By far, the most common way of doing it, it's convenient. It is convenient because it is easy to store. One text, one vector, you can store it in a row of a database, right? Once you have broken up a text into chunks, you can have a unique chunk ID pointing back to a parent document ID, and that chunk has associated with it a little bit of text and a vector. Are we together so far? And that vector, magically, you store it in a vector database. FAS, we talked about the FAS, approximate nearest neighbor index. To the first approximation, consider that the core of a vector database is the approximate nearest neighbor implementation. So you have been using a vector database, right? Remember, a vector database stores only vectors. And therefore, what you did is you invented or reinvented your own vector database. Now the question comes, what happens next? Suppose the query text comes, you convert the query into a vector, you do a k nearest neighbor search, you get the neighborhood vectors in that space, and you ask yourself, what do these vectors represent? Which pieces of text do they represent? By pulling out those vectors that they represent, I mean, the text that they represent, now you say that you have search results, isn't it? You inverse map from the vector back to the text. Now, remember, when you inverse map, it is not a mathematical operation. You cannot do that. From a vector, it's very, very hard to get back a reconstructed text. What you instead do is, before you save it in the database as such, that this text and this vector, they go together. So you just do a lookup, inverse lookup, reverse map lookup, and you get your text ID. Those text IDs become your search results. So yeah, you did that. If you look, remember in phase one, phase two, that's exactly what you did. Remember in a CSV, what did you do? You stored a chunk, chunk ID, chunk text, chunk vector. So when you get a vector back, you can look up the text, isn't it? You can look up the text. So those are your search results. While this is the first version I taught you in the last 2 weeks, this itself represents perhaps the profoundest shift and biggest revolution in the search industry. When these methods came out, when people realized that you could use transformers for this, the initial iteration was to do something much more expensive. What you would do is you would send a query and a document together into a transformer, into a BERT. And using the CLS token, you would do a softmax. You would say, how similar were these two statements? What was wrong with that approach? Do we remember? It was horrendously expensive because you had to compare a query against all the documents. If you have today web scale companies, they have think like a tiny web scale company would have 100 billion items, right? And a reasonably large web scale company would count it in trillions, right? And this is reality. This is not hyperbole. Typically, you partition up into different indices. So maybe it's just a couple of 100 million documents. And even 100 billion, you cannot compare a query against 100 billion and pass it through an entire transformer network at query time, at inference time, and realize that, oh, these are the nearest neighbors, right? Horrendously expensive and a computational disaster. Nevertheless, knowing how valuable this approach was, what a radical shift, radical improvement it gave to the query results. The history is both Google and Bing, the leading search giants, right? By the way, after Google, has anybody even heard of Bing? No, I'm kidding. Okay. So, well, number one and number two, they both jumped into this approach, realized it's very expensive, till the paper Sentence Bird came out, which basically said, here is a way to cheapen the operation. You're doing comparisons. Don't compare the text. Instead, compare their vector embeddings and train the vector embeddings using contrastive loss. So make the vector semantically aware, right? And if you look at that's why if you look at the document, the write-up that I gave you, I call it the latent space of meanings, the metropolis of meanings, right? It's literally that. Those vectors are points in an abstract world where things that mean similar, sentences that mean similar things, or documents that mean similar things are adjacent to each other, right? Or another simplified way of saying it is birds of a feather flock together. Go ahead. Absolutely, absolutely. Right. Yes, indeed. And they did. And in fact, this one idea was such a revolution. See, if you look at companies, right, the startups, the things they happen, behind them is not a million scientists doing a million different things. Usually, there is one or two good ideas, and those ideas are simple ideas. This semantic search was a revolution. All of these things. So, for example, what is Spotify? You go to Spotify and you get your recommendations and things like that. What are they using? From every public thing that has been revealed, they are using just this. That's what they are doing. What are all the social media giants using? The Facebooks, the all of these things that exist, Snap or TikTok, and so whatnot. They all are doing this. I happen to know that they all do that, right? Because they have revealed some things in public domain and their architectures, etc., and they acknowledge it. So this was quite a revolution. In fact, recommender systems pivoted. Recommender systems have been going through evolution, right? If you remember, the Netflix prize was a game changer for the recommender system way back in the early 2000s. It was won by the alternating least square implementation, which was a matrix factorization approach. When you look back through the lenses of today, it looks so basic. And yet, it was a revolution in recommender systems. If you remember, in the between 2000 and 2010, Silicon Valley, with all its vaulted innovativeness and everything, it was nothing but a cottage industry with every group of 5, 10 people doing a startup, well funded, doing what? Just using that alternating least square method or its variants to do recommendations. Recommendations for advertising, recommendations for e-commerce, recommendations for this, recommendations for that, right? Those things have been evolving over time. Those things matured more and more and more. But the next big shift that came in recommender systems, and we will cover it in this course, the two biggest shifts that came from two directions. One was semantic search. What you're doing is literally the foundation of a recommender system, right? And the second thing, today, it's a basis of it, embeddings. And the second thing that happened was the use of graph neural networks, which also is another more advanced way of creating vector embeddings. So the recommender world today is all about this, what you have just learned. Search and recommender systems, two of the most powerful things that drive our world, are based on what you just have already learned in the last 2 weeks. No, I mean this technology, this entire technology of creating vector embeddings, storing the vectors and retrieving the nearest neighbors. Semantic search. The word we use is semantic search. Right
Asif,
now,
sorry,
Suren, one
Asif,
second. Hold on
sorry.
to your question. I want to finish this thought. So, guys, what is it made up of? Semantic search is the innovation. Approximate nearest neighbor has been around for decades. It's been getting better and better. So, for example, FAS is a recent breakthrough that makes it's sort of a computational breakthrough. It makes it massively scalable and parallelizable, the search for k-nearest neighbors. And there are many variants. There is SCAN, Google has SCAN, there is HNSW, and many of these can be hybridized with each other. So if you look at the FAS implementation, you can hybridize these implementations, indexes together. And all these companies that came up called vector databases, what are they doing? At core, they give you two services. Remember, at this moment, you have to store the text and the embeddings. They give that to you as a service. So you don't have to have your own FAS index and a little database of your own. They say, hey, don't worry, we'll take care of it for you. The other thing that you do is documents often have metadata associated. This is from the finance department. This is from HR, talent management, right? So on and so forth. So when people query, sometimes they are domain specific. And so you want to filter your query results to specific domains. When you do want to filter your results to specific query domains, then there are two ways of doing it. The way that you could do it is that you get all the results and then you look at the metadata, because in your table chunk, you could now also have metadata column, and then you can filter by metadata, isn't it? Yes. That was easy. All you had to do is add one column. Think about it. Yeah. No, no, no. You get the vectors and then you filter them down. That is all it is. That's all these guys also are doing, essentially. Right? Most of them are doing that, except for Qdrent, which does something smarter, which actually uses a graph theoretic argument to infilter in the processing itself. Right? Qdrent. And you will learn Qdrent today. It's a topic of today. No, no. So I'll come to that. Hold that thing for the question answer. Srirang, you had a question.
Yeah, so no, I think all here, the people on the online were losing the context. I appreciate if you could repeat the question that came, because there was a good discussion, but we kind of lost the context as to what the
The
question
question
was.
we were all trying to figure out how to save the metadata.
Mhm.
And I'm saying that if you have domain specific, let's say that you have a document, it's about finance. What can you do? You maintain a table called documents where you say document ID 1, right? And then you can have a subject called finance.
Mhm.
Suppose you want to query only into finance, what will you do? You get all the chunks that match the candidate search results, and then you filter them down to only those chunks whose subject is finance, whose parent document subject is finance. As simple as that. Does
Makes
that make
sense.
sense? And so vector databases are things that give you principally two qualities. They give you this whole thing for you free. And they manage the ends. And the third thing they give you is, see, they make it into a server. Databases are servers, multi-user experiences. And when you home grow your own server, actually in the first version, the first two iterations of this bootcamp, I made them make the entire vector database, the whole server, ability to take REST calls and everything from scratch. And I noticed that people got very tired, right? So I leave that as an optional exercise for this batch. I won't get there. What I will do is I will give you guys a full-blown implementation, the code for a full-blown implementation. You can at least read that code. You don't have to implement the whole thing from scratch, because from experience you get very tired. Instead, today I'll introduce the vector databases. In particular, we'll talk about Qdrent. And what you will realize when you play with Qdrent is that it is doing exactly what you were trying to do. There are other things that these things do. Of course, they do it at a much more production grade scale. They give you the ability to both insert and query at the same time. They do the management of the indices much better than you can, right? They merge, they do parallel indexing and so on and so forth. So they have all of those facilities. Next. So that was, I hope, a summary of semantic indexing. Go ahead, Sanjay. Oh, CLS is okay, I will cover CLS, maybe the BERT paper. I've covered attention is all you need. I haven't covered the BERT paper. Right? So today I'll cover the BERT paper. It's for today. So, and when we do that, we'll talk about the CLS. But just think of it as a token that you put in front of the sentence. And if this token itself has no meaning in the English language, then other tokens, when it pay attention, wouldn't know what to think of it. But this token, when it pays attention to every other word, it pretty much will get the essence of the sentence. Yes, that's pretty much it. It gets the essence of the sentences. That's what it is. So, guys, that's a recap of the last time. I hope all of you know the phases of the homework. Right? It is there. And I want you guys now to finish the phases of the homework. To motivate you, there are some very powerful machines already with your team names and everything. But you won't get it unless you prove to me that you have finished at least phase 3. Fair game? How many of you have done phase 3? Okay, only one team gets a machine. Right? Outer space. No, no, no. There's a reason why AI is done on massively powerful machines. So we'll do it that way. All right, guys. So let me give the scope for today. Today, we are going to pivot and do two things. In the research paper reading, we'll read BERT. That's a research paper. We are also, time permitting, going to do one more research paper, which I won't mention now, but we'll first start with BERT, see how far we gain traction with that. The second thing we'll do is we'll do prompt engineering, a topic. We'll pivot away and do something. Prompt is something all of you are familiar with, isn't it? But we'll learn to do it thoroughly. Well, reasonably enough, so that we can put semantic search with prompts and LLM to create something called RAG. A moment about RAG, retrieval augmented generation. I will talk in the next, I'll take a 5-minute break, and after that, I'll talk about retrieval augmented generation, which is a core topic. I'll explain that. Prompt is easy. We'll learn it by doing it. And today, just as for the last 2 decades, the poster child of machine learning, the only application that was de facto most used was the recommender system in the industry, right? Commercial industrial use, wide scale use was of the recommender systems, right? It was, if you were good with recommender systems, it was an evergreen topic. Even today, it's an evergreen topic. You'll always have a job, right, in AI. Most, if you threw a stone at a room full of AI engineers, right, there was a 90% probability it would hit somebody who has been working or has worked previously on recommender systems, right? So that's hot. But these days, one new topic that has emerged from generative AI, and which is, in my opinion, going to dominate the next 10 years, this decade, and it will evolve. It started with a very simple version last year. What was state of the art last year when it came out? Actually, it came out in 2022 itself. But what we consider the state of the art then, in the last 2 years, is today considered baseline, right, or too elementary. Companies came, they rose, they did that baseline, what you today would call baseline implementations, and became wildly successful. Everybody else was waiting on the fence to see whether this idea would take off or whether it was a hype. They realized, and because business people don't know, they don't know computer science, they don't know AI, and for some reason, they don't show up at support vectors to learn it. No, I'm kidding, right? So, so yeah. So once they realize that this is not a hype, this is not engineers hyping up something, this is for real. This year has been the year massive investments are going into RAG, production level investment, to such an extent that it's hard to find a company that's not doing RAG. Whether it's a pharmaceutical company, whether it's a logistics company, whether it's a airlines company, whatever it is, customer support is a very, very obvious example. It's hard to imagine an enterprise that doesn't have customer support. Most customer supports are now moving to RAG because from a bottom line saving, it's just a no-brainer. No-brainer, right? How it saves. And I'll explain how, what it all means, RAG. And then we are also entering the world, the next success, and I'll give you a touch of it, though we won't go there till the very end of this course, of something called autonomous AI agents, right? So how many of you have seen the movie Matrix? That is what autonomous AI agents were, right? So it turns out that what was movie then has become reality today, right? And it's turning the world on its head completely. So we will get there, but that's a topic for today. We'll get to. So if you thought semantic search was profound, impactful, what I'm going, RAG is having such a dramatic effect and such a widespread effect that I call a course that I teach, which is, by the way, starting in the second half in October. And by the time those of you, if you get very interested in RAG, you're welcome to go register for that topic. That course is provocatively called RAG to Riches, right? And literally, it is that. Many consulting groups and many small startups are finding that the shortest path to riches is to start doing RAG and implement it for enterprises, because every enterprise needs RAG, right? So we'll come to that. I'll just give you guys, so this was a summary and this is a view of what we are going to do. To summarize, today we are going to do prompt engineering and RAG. I will introduce RAG and then I'll go back to prompt engineering. We'll read a couple of research papers. I will give you a lot of time, guys, today for labs. Like I'll set up your machines, right? I'll give you guys access to the machines. You will install Tailscale on those machines. You guys know what Tailscale is? Yeah. You will create your group Tailscale account. And when you do that, you need to make sure that I'm a member of it. Right? So I can keep an eye. So which means that because I think 5 or 6 users are allowed, your team cannot be too big. Otherwise, you'll have to pay for it. It's not too much. It's $4 or $5 a user, but try not to make your team too big. Stay within the free envelope. And that's our scope for today, the work for today. So guys, I hope you brought your fresh minds because believe me, today's topic of RAG is the topic in generative AI. It's the key topic of generative AI, right? I will take a 5 minutes break. I forgot to turn on the AC. I'll do that and do it. What's that? Today, both. Yeah. All right, guys. So I'm going to pause this recording. This was a recap and we'll start again. Guys, in no more than 5 minutes, we'll start. Yes. So coffee should be ready or I'll go make it ready if it isn't ready. And I apologize for the mess. I came late and the coffee wasn't there.